Hi folks, this episode of the microcontroller tutorial series, I want to do something that's kind of strange. Instead of connecting a digital pin or digital input to your microcontroller GPIO digital input pin, actually connect one of my bench power supplies, feeding some basically arbitrary voltage into the microcontroller and see what happens. And yes, that's something you're supposed not to do. When I was an undergraduate student sitting in a hardware lab, playing around with oscilloscopes for a change, I was explicitly told, like everybody else, you're not an electrical engineer, you're not even doing this as a secondary subject, so for you there are exactly two voltages, there is 0 and 5 volts, ground and VCC at that time, and everything else is out of bounds. Basically means I'm gonna do it anyway. And there are a number of interesting effects to see, and the result is not quite as straightforward as you might think. So let's see what happens there. And here's the setup. Basically the same software, the same LEDs on the microcontroller boards, but in this case I feed input from the bench power supply through the protective series resistors into the microcontrollers, and I also hooked up a multimeter so you can actually see the voltage. And the only reason why I use the bench power supply is not because I want to show off, doesn't make much sense, but because I don't have any proper 10-turn pot lying around which I could use for this. This just provides me some very nice control over the voltage that I feed into things. If you want to do this yourself and have a decent precision pot or anything like that lying around, works just as well. You see, we're at about 800 something millivolts. That's about as low as my bench power supply goes, and all the LEDs are turned off. So the microcontrollers read false or 0 or low or whatever on the input pin. And when we turn this up at something at about 1.2 volts, something strange happens. The LEDs on the PIC kind of start to flicker. They're not really supposed to do that, but well, we'll have to take a look at that later on. Once we hit about 1.25, 1.26 volts, they stabilize and turn on completely. And when we keep going, at, where is it? At about 1.85 volts, the LEDs on the MSP430 turn on, and they just go bang on, and that's it. And we keep going at 2.55 volts, the LEDs on the MSP430 also turn on. Okay, that's fine. Fun thing is what happens when we reduce the voltage again. Now we go way beyond 2.5 volts and the LEDs on the 80 mega stay on. And they only switch off again at about 2.2 volts, not 2.5 something. With the MSP430, it's kind of similar. We go way beyond the voltage where they actually turned on before. 1.5, and at 1.45 volts or so, they turn off again. With the PIC, let's see what happens there. Yeah, at 1.25, 1.24, they start to flicker, and we lower the voltage a bit more. They eventually turn off. So what did we see? Now, for whatever voltage, well, we have ground somewhere like here, and VCC somewhere like here. You might expect that there is some kind of threshold value below which we consider everything 0 or low or false or whatever, and above which we consider everything 1. What we observed, however, at least with the MSP430 and the 80 mega, is something different. If our voltage goes up, we have a threshold here, which is called the upper threshold, big surprise. Threshold. And we consider everything above that as 1 and everything below that as 0 for rising edge. When then the voltage goes up, and when the voltage goes down, we have a significantly lower threshold. For where make the distinction between 0 and 1. And why is that? Well, it makes the signal we input much cleaner. We don't have any unnecessary, or we have less unnecessary transitions, because what happens if we just had a single threshold? It would look like what we've seen on the PIC. We increase the voltage at some point very close to the threshold. Just the noise on the line, and there's always noise, would make the input flip between 1 and 0 all the time. Whereas if we use this, and the circuit you use for this is called a Schmitt Trigger with double T. Ensures that even if our input is kind of noisy, we only switch from 0 to 1 once we go above the upper threshold, and we only go down to 0 again once we go below the lower threshold. So this Schmitt trigger makes the input much less susceptible to noise. How important this is, there is a very nice video Dave Jones recently did on the BIVBlog, where he actually fed a slowly ramping up input to the clock signal of a counter chip. And you do that, which is admittedly kind of a worst case scenario, you get a really messy result. Putting a Schmitt trigger in front basically solves that entire problem. He also explains how to build these using an op-amp and whatnot. So really interesting. I'll link it in at the forum at www.stepladder-it.com/bivblog/49. And he explains how it works. But that still leaves one question, namely, what's wrong with the PIC? Obvious explanation is I accidentally killed it. Despite using these current protecting series resistors and everything, I managed to damage that microcontroller. Obvious, explains what we've seen, but that doesn't mean it's right. To figure out what really happened, once again, we have to take a look at the associated datasheet for that device. And here's the datasheet, and the trick here is to search for Schmitt trigger. And that's where you want to remember that it's written with double T. And there's already something. Pinout description continued. Okay. RA, whatever, RB. RB0, that's the pin we're using for whatever they call it, R whatever. And here's the problem. Input type says TTL, not Schmitt Trigger, ST. If we had used pin C0, that would have had a Schmitt Trigger. So once again, the PIC has a kind of a surprise for us. It doesn't have Schmitt Triggers on all its inputs. And that's about not reading datasheets beforehand. If you need a Schmitt Trigger on an input, use a different pin. So the Schmitt Triggers on the microcontrollers are pretty much standard, except for the PIC, which once again has this little surprise that it is missing a feature on some pins that's pretty much standard everywhere else. Keep reading the datasheets, can't help it. Otherwise you might actually wind up with these sorts of surprises. And what this should show is that even if we have some kind of noisy real-world input, the microcontrollers using the Schmitt Trigger can actually deal with it quite nicely. And we've also seen what happens if we don't have one. You've seen the PIC flicker like mad because of some line noise when we got somewhere near the single threshold it uses. Right? That's what I wanted to show you about real-world input and Schmitt Triggers and whatnot. And hope you liked it. Give it a try. It's real fun to see what happens. There's one more question. Where exactly are the thresholds? And again, you have to take a look at the data sheets. It depends largely on VCC. Shouldn't be that much of a surprise. It depends on temperature, at least according to some data sheets. And of course, device tolerances. Like we never had this problem with electronics before, right? So if you build something that does input, take a look at the data sheets, check that the thresholds actually match the input you actually have available. Otherwise, you might get some really strange effects. If the input voltage is higher than the microcontroller can handle, you normally use a voltage divider or similar to ensure that the input is reduced to some sort of level that doesn't get into the magic smoke range of input voltages for the microcontroller. If you want to make it really flexible to all sorts of input, you might actually use a resistor plus a Zener diode. Beyond the scope of this, we're probably going to come across something like that in a future episode, so we'll talk about that. Of course, if the input signal is too weak or at wrong voltages, you might actually need some kind of amplifier to boost the voltage difference to something the microcontroller can handle. Plenty of things to do about that, and when it comes to boosting the input voltage, the problem is pretty similar to switching larger loads on an output pin of a microcontroller, so we're going to talk about these amplifier things another time. Right now, I guess that'll do for one episode. And yes, in case you wonder, I'm still wearing the same t-shirts. I've actually managed to record 2 episodes in one day. Really proud of it. Probably going to take me weeks to find the time to edit and upload and these videos and then do the page on the BIVBlog webpage. But we'll see. Anyway, if you have questions, comments, whatever, come to the forum as usual as www.stepladder-it.com/bivblog/49, and well, hopefully I just keep recording yet another episode, so it'll be 3 episodes in one day, I hope. And in any case, see you again soon.